In this video, we'll talk about representation of a complex number in polar form. How to represent a complex number in polar form, right? Now, I have a complex number in rectangular form. Z is equal to A plus IB. This complex number is in rectangular form, or you can say Cartesian form. Rectangular or Cartesian. So we can actually convert a complex number in rectangular form to a polar form. First of all, I want to represent this vector, that is this complex number, on an Argand diagram. The real part corresponds to the x-axis, and the imaginary part corresponds to the y-axis, okay? So this is the real part, and this is the imaginary part. This is positive as well, okay? These two axes are negative. Now, I want to write this pictorially. Z equal to A plus IB. Let us assume a point on the positive real axis, A. That's what we have here. Let us assume a point on a positive imaginary axis, B. If we plot this point, let's say the distance of the complex number from the origin is called the modulus of the complex number. We usually use arrow to denote modulus. Confirm an angle here of theta. Arrow is called the modulus. Arrow is the modulus of the complex number. And theta here is called the amplitude or the argument. Theta is the amplitude or argument. Alright, this line corresponds to B. Okay, so distance from the origin to this point is the same as this distance, and this distance is A. Let us determine the modulus of this complex number. This is a right angle triangle, of course. So by Pythagoras rule, arrow squared is equal to A squared plus what? B squared. So if we take the square root of both sides, the square takes away the square root, arrow will be equal to the square root of A squared plus B squared. From here, we can get three trigonometric ratios: sine, cosine, and tangent. Sine theta is opposite hypotenuse, which is B over arrow. Sine theta is equal to B over arrow. Cos theta is adjacent hypotenuse, which is A over arrow. Cos theta is equal to A all over arrow. Also, tan theta, which is opposite adjacent. Tan theta is equal to B all over A. So, if I'm going to use this ratio, tan theta equal to B over A, means that theta is the tan inverse of B all over A. Now, from here, if I make B the subject of the formula, B is equal to arrow times sine theta. That's arrow sine theta. And from here, if I make A the subject, A is equal to what? Arrow cosine theta. Okay, take note of this. So, in polar form, I can write Z equal to A plus IB as Z equal to A. A is arrow cos theta. Arrow cos theta plus I times B. That is I times B is arrow sine theta. Arrow sine theta. Arrow is common to both. If If I bring arrow out, we'll be having z equal to arrow in brackets cos theta plus I sine theta. And we call this the polar form of a complex number. Alright, let us proceed and see how some complex numbers are represented in polar form. The first question here is to express z equal to 4 plus 3i in polar form. The complex number here is in rectangular or Cartesian form. So let us express it now in polar form. The first thing I'm going to do is to have a sketch of this on an argand diagram. The real number is 4 and the imaginary number is 3i. Let's fix it here, 4, and let's fix 3 here, 3. Alright? This imaginary part is positive, so I'm dealing with the positive imaginary part. The real part is also positive, and this is the positive as is for the real number. Okay? 4 plus 3i meets at this point this arrow. So we also have to determine the argument, and the argument is measured from the positive real axis. Alright? Remember the polar form that says z equal to arrow cos theta plus I sine theta. So we need arrow and we need theta. Remember that the modulus is calculated as the positive square root of a squared plus b squared. A is 4, b is 3. That will be 4 squared plus 3 squared. Okay, so we have 4 squared is 16, 3 squared is 9. 16 plus 9 is 25. So we have the square root of 25, which is equal to what? 5. So the modulus is what? 5. Remember also that tan theta is equal to b all over a. Okay, so theta is the tan inverse of b over a. Theta is the tan inverse of b all over a. A is 4, b is 3. Okay, the argument will now be the tan inverse of 3 over 4, since b is 3 and a is 4. And the tan inverse of 3 over 4 is 36.869 degrees. Alright, the complex number 4 plus 3i is in the first quadrant. This is the first quadrant. And our angle here lies in the first quadrant as well. We'll make use of it. So the polar form will now be z equal to arrow is 5 in brackets cos theta. Theta is 36.869 degrees plus I sine 36.869 degrees. Take note, I can as well take this back to the rectangular form. Cos 36.869 is 0.80000. That's 0.8. Okay? Plus I sine 36.869 is 0.599. Alright? So if I expand this bracket, I will have z equal to 5 times 0.8, which is equal to 4. Then 5 times 0.599. And that is 2.995. If I approximate it to the nearest whole number, I will have 3i. And that is what we have as the question. Okay? So, polar form can also be transformed back to rectangular form. Let's see the second example. Let us express minus 5 plus 2i in polar form. This vector is in the second quadrant. We have minus 5 plus 2i. The real part is negative. This is the negative real part. And here our imaginary part is positive. This is the positive imaginary part. So this is the second quadrant. Alright? So let's say from here to here is of 5, which is minus 5 as we have it there. And from here to here is 2. Alright, let's see 2. The modulus, which is arrow, is the positive square root of a squared plus b squared. A is minus 5 squared, plus b is 2, that's 2 squared. Minus 5 squared is 25. 2 squared is 4. So 25 plus 4 is 29. 29 is not a perfect square. That is, it does not have an exact square root. So we can just leave it like this, okay? This angle here is called the reference angle, okay? The reference angle, let me say theta. Let us determine the value of the reference angle that we have here. Tan theta, which is the reference angle now, is equal to what? B over A. Now take note, B is 2, okay? A is minus 5. I'm going to make use of the positive of the numbers. I'll make use of positive 2 and positive 5. I will neglect the minus. Any minus that exists, I will neglect it. So, the value of the reference angle will be the tan inverse of 2 over 5. And that will be 21.80 degrees. 21.80 degrees is an angle in the first quadrant, but our vector is in the second quadrant. The argument is measured from the positive real axis down to where I have the line, okay? So it is this angle here that I'm going to make use of. So since our reference angle is 21.80, the argument, which is theta is equal to 180 degree minus the reference angle. This must be noted. So determine the argument in the second quadrant, subtract the reference angle from 180. Okay? We'll see what will happen when we get to the third quadrant. So theta is equal to 180 degrees minus, what is the reference angle? 21.80. 21.80 degrees. That is equal to 158.2 degrees. This is the angle in the second quadrant. Therefore, in polar form, minus 5 plus 2i is equal to this. Z equal to minus 5 plus 2i in polar form is equal to arrow, and arrow is what? Root 29. Root 29 in brackets cos theta, which is 158.2 degrees, plus I sine theta, which is the same 158.2 degrees. Yes, we can take this back to rectangular form. Root 29 times cos 158.2 degrees is minus 5.000. So that is actually minus 5. Root 29 times sine 158.2 degrees is 1.9998, which is equal to, if we round it up to the nearest whole number, 2. So 2 times I, 2i. And that's what we have here. So it is possible to convert back from polar form to rectangular form. Let us see the next question. This time around, the complex number will be in the third quadrant. All right. Let us express z equal to minus 3 minus 4i in polar form. If we sketch that on an agar diagram, we are going to have this, okay? Both real and imaginary are negative, okay? So this is the negative real axis, and this is the negative imaginary axis, all right? And the reference angle is always made with the horizontal. Take note of that. But the angle we are looking for must be in the third quadrant. And that angle is measured from the positive real axis down to this line. You get it? This is the argument, theta. We'll see how we're going to get that. What is the modulus of this number? The modulus arrow is equal to the square root of minus 3 squared plus minus 4 squared. Alright. Minus 3 squared is 9. That's 9. Then minus 4 squared is 16 plus 16. 9 plus 16 is 25. And the square root of 25 is 5. So the modulus is equal to what? 5. Now let us determine the reference angle. Okay? The reference angle, which is the angle that is made between this line and the negative real axis. So the reference angle will be the tan inverse of b over a. A is minus 3, b is minus 4. I'll just neglect the negative signs. 4 all over 3. The tan inverse of 4 divided by 3 is 53.13 degrees. 53.13 degrees. This angle is an angle in the first quadrant. But our vector here, the complex number, minus 3 minus 4i, is in the third quadrant. To determine the angle in the third quadrant, we will add 180 degrees to the reference angle. In the second quadrant, what did we do? We subtracted the reference angle from 180. In the first quadrant, the reference angle is the same as the argument. Here in the third quadrant, we are adding the reference angle to 180 degrees to determine the argument. So the argument, theta, is equal to 180 degrees plus the reference angle, which is equal to 180 degrees plus 53.13 degrees. So the argument is equal to 180 degrees plus 53.13 degrees is 233.13 degrees. 233.13 degrees. This is the argument. Therefore, the polar form of this complex number, z, is equal to arrow, which is 5, in bracket, cos theta, which is 233.13, 233.13 degrees, plus I sine theta, 233.13 degrees. This is it. So let us see the last question, and that vector falls under the fourth quadrant. Keep watching. Let us express z equal to 4 minus 3i in polar form. 4 minus 3i lies in the fourth quadrant. The imaginary part is negative, and this is the negative imaginary part. The real part is positive. This is the positive real part. So the vector lies in this quadrant, which is the fourth quadrant. This is first, second, third, and fourth quadrant respectively. Alright? The reference angle is made between the line and the horizontal. But the angle we are looking for must be in the fourth quadrant, since the vector is in the fourth quadrant. And that angle is measured from the positive real axis down to this line. Let's start by getting the modulus. The modulus is the positive square root of a squared plus b squared. A is 4, that's 4 squared. B is minus 3. Minus 3 squared is 9. 4 squared is 16. 16 plus 9, and that gives us 25. So root 25 is 5. This is the modulus. Now, what is the reference angle? Is the tan inverse of b over a. B is minus 3, but we'll make use of the positive plus 3. So 3 all over a is 4. Okay, plus 4. And that is 36.869 degrees. This is the reference angle. 36.869 is in the first quadrant. Our complex number is in the fourth quadrant, so we need an angle in the fourth quadrant. So to get the amplitude or the argument, since the vector is in the fourth quadrant, we are going to subtract the reference angle from 360 degrees. Remember, in the first quadrant, the argument is the same as the reference angle. In the second quadrant, the argument is equal to 180 minus the reference angle. In the third quadrant, the argument is 180 degrees plus the reference angle. And now, in the fourth quadrant, the argument is 360 degrees minus the reference angle. That will be 360 degrees minus 36.869 degrees. So what would this give us? 323.131 degrees. This is the amplitude or the argument. So in polar form, Z is equal to arrow, which is 5, times cos theta, which is 323.131 degrees, plus I sin theta, 323.131 degrees. Remember that it is possible for us to take this polar form back to rectangular form. Let's just do that. Okay, this is the polar form. Take notes. So, 5 times cos 323.131 degrees is 4.000047. And that is 4 to the nearest whole number. Then, 5 times sine 323.131 degrees. And that is minus 2.99993. So we can just say minus 3. If you round it off to the nearest whole number, that's minus 3i. Alright, this is how to change a complex number in rectangular form or in Cartesian form to polar form. I hope you enjoyed the video. Remember to subscribe, like, and share the video to your friends and to your classmates. I'll see you in the next one. Keep watching.